In this lesson, we will discuss some important thermal properties of matter. When heat is supplied to an object, what are the changes that you can expect in the object? Well, you know that heat is a form of energy. That means when you give energy to matter, the atoms and molecules will behave differently. Is that right? Because heat is a form of energy. Now, what kind of different behavior will atoms and molecules have? Their kinetic and potential energies can change. That means molecules and atoms will vibrate or move about with larger amplitude. When molecules want to oscillate with larger amplitude, they need a larger space to occupy. So one of the most prominent effects of supplying heat to an object is thermal expansion. An object expands when heated. All right, we will start looking at expansion, thermal expansion first. Heat supplied to a material will increase the internal energy and causes the molecules to vibrate with larger amplitude. As a result, each molecule now takes up a little more space than it had occupied earlier, which results in the expansion of the material. Now, as a result of expansion, its length, area, and volume will increase. Now, if an object is like this, most dominant change will be an increase in length. On the other hand, if the object is a flat surface, the most dominant change would be the change in area and obviously a change in volume. Well, if an object increases its volume without changing its mass, that means its density will change. So heating an object can change its density. What do you think? What kind of density change can occur? Is it an increase in density or a decrease in density? Well, think about it. Now, we will consider each of these changes separately. Let's start looking at the change in length when heat is supplied to an object in the form of a rod. Okay. Now, here I have a rod of original length L0 at a temperature T0, and its length increases by a small quantity delta L when the temperature is increased to T sub F. Now, in future, in place of T0, we will use T1, and for TF, we will use T2. Temperature increases from T1 to T2 or T0 to TF. So the length of the rod at the temperature T0 is L0 and its length at a temperature TF is L0 plus delta L. When an object is heated, its length increases. The increase in length delta L, what are the factors on which the increase in length of an object depend on? If I start with a longer rod, the increase in length will be greater. Is that right? And also, if I heat it through a greater temperature, the increase in length will be greater. So these are the two dominant factors on which the increase in length depend on. So the increase in length delta L is directly proportional to the original length and the change in temperature. Can you write that as an equation? We can write it as delta L is directly proportional to L0 delta T. And you know by now a direct proportion can be replaced by an equal sign adding a constant. So delta L equal to alpha L0 delta T, where alpha is a constant for a given material. It is called the coefficient of linear expansion, or sometimes it's called the linear expansivity. Alpha is a constant called the coefficient of linear expansion. And what is the value of that? If you write an equation for it, alpha equal to delta L divided by L0 delta T. So what is alpha? Can you give me a sentence describing alpha? Alpha is a measure of the increase in length per unit length per Kelvin rise in temperature. In other words, if I take a rod of length 1 meter and heat it by 1 Kelvin, the increase in length at that time will be a measure of alpha, the coefficient of linear expansion. It is a measure of the increase in length per unit length per Kelvin rise in temperature. Tell me, what is the unit for measuring alpha? Can you look at this equation and tell me what is the unit for measuring alpha? If you look at the right hand side, delta L is measured in meter. The original length L0 is measured in meter, so the meter and meter will cancel. The only unit that survives is Kelvin on the denominator. So alpha is measured in a unit called per Kelvin. There you are. So the unit of alpha is per Kelvin. Let's now talk about an experiment to measure alpha. That will be an experiment that you will be doing in the lab. Now here is the experimental setup we will use to measure the value of alpha for a rod like this. In fact, this is part of that experiment. I have taken from one of those experimental kits to use it as a rod to point on the board. Well, if you look at this, this is called a steam jacket. Now, I have that equipment right here. This is the steam jacket. I can take it out. Now, the rod whose alpha is got to be measured, you start by measuring its initial length L0 and then insert it inside the steam jacket. There you are. And keep it back in there. And what is the specialty of this? Now, the rod is now in contact with this screw, which is fixed. That means the rod cannot expand that way. And on this end, you have a micrometer screw, which can be turned so that a space can be left in here. You can see where I'm pointing. There is space and the rod can expand there. Now, once you have a space there, you can pass steam through here. The steam will go into the jacket and then out through the other end. And after passing steam through this for about 5 or 10 minutes, the rod will expand. And now work the micrometer screw back. You can measure the increase in length. So once you know the increase in length, the original length, and the rise in temperature, we can calculate the value of alpha. Is that right? The coefficient of linear expansion. So in the steam jacket, you can use the thermometer to measure the initial and final temperature. You can measure the initial length before you put the rod in there, and the micrometer can be used to measure the increase in length. Okay, so the length of the metal rod L1, as I had told you, in place of L0, I'm going to use L1. The original length at T1 degrees Celsius is L1, and that is measured at the room temperature. And the arrangement shown here, we will use that to measure the length L2 at a temperature T2 after passing steam through the jacket. And once you have those measurements, we have delta L equal to L2 minus L1 and delta T equal to T2 minus T1, and that will be enough for us to make our calculation. Alpha equal to delta L divided by L1 delta T, and that will be delta L is L2 minus L1 and delta T is T2 minus T1, and this will give you a measure of the coefficient of linear expansion. Let's now solve this equation for L2 minus L1. Can you do that? Alpha equal to L2 minus L1 divided by L1 times T2 minus T1. Therefore, L2 minus L1 equal to alpha multiplied by L1 times T2 minus T1. And in this equation, we can solve for L2 if you move L1 to the right side. You have L2 equal to L1 plus alpha L1 T2 minus T1. I can factor out an L1 on the right hand side. Let's do that. That will be L1 times 1 plus alpha delta T. L2 equal to L1 times 1 plus alpha delta T. A very important equation which will help you to find the length of this rod at a higher temperature if you know the original length at T1 degrees Celsius, the change in temperature, and the coefficient of linear expansion. We will use that to solve problems. Well, let's now talk about the change in area. Now, if you have an object like this, for example, a flat object, when it is heated, its length will increase, its width will increase. As a result, its area will increase. Change in area, and we can actually define similar quantities that we defined for linear expansion in this case as well. Similar expressions can be written for the change in area with temperature, and what are those? The change in area delta A is directly proportional to the original area and the change in temperature. And when you write it as an equation, it becomes delta A equal to beta A delta T, where beta is a constant. And what will you call that constant? Well, you can call it the coefficient of area expansion or area expansivity. Beta is called the coefficient of area expansion.